He's Professor Dr. and he has been an important figure in the history of science in Turkey. And to say the least, he was for many years the vice chairman of TÜBİTAK, and he had also been the chairman of TÜBİTAK himself. And I was fortunate enough that in my undergraduate year I had taken quantum mechanics course, both as a scientific figure and as a lecturer. He is one of the people who I take as one of my role models. Unfortunately, he passed away 2 days ago. This morning there was a funeral, and I feel happy for myself that I have been fortunate enough to meet him, but at the same time, most of you will probably not be able to meet him. Nevertheless, some of his lectures on quantum mechanics, they are available on YouTube. If you go to YouTube and search for his name, you will find his quantum mechanics. Unfortunately, it is the second quantum mechanics PhD level course. We didn't have enough time to record all his lectures, or you can go to the Made to Open Courseware website, where you can also have a list of his videos. And when you are at that level, when you learn some quantum mechanics, you can still follow his lecture. And I strongly recommend you to follow his lectures. These are great lecturers. Okay, so let's go back to physics, the thing that we have been studying. Now, if you remember, we are still applying Newton's laws, Newton's first set of the 3 laws of Newton to study the behavior of dynamics. This week, today and next week, we will be changing kind of our approach. Up to now, we were interested in how to find the time dependence or the position and the velocity. But at least in some cases, and that is too much information. We don't want to know that much information. Just to say, give one example, if you remember. Okay, so this is roller coaster example. Suppose you are building a roller coaster. Of course, you would like to know at what time the roller coaster will be at one point, but there is one more important information you would like to make sure that when it is at this point, it should have enough velocity. It should have enough speed, otherwise it will just fall down. We don't know when we don't have to know when it arrives there, how long it takes it to arrive there, but the only thing we want to know is how to find the speed at that point if we know the speed right here. It is possible to solve it in a differential equation, and that's what we will be aiming at. But before we go, do you have any questions about the Newton dynamics of the applied Newton's laws or anything we have covered up to now? Any questions? Do you have any? Okay. So, let's do an example to motivate some of the definitions that we will be discussing today. Let's just, for simplicity, take the one-dimensional example, one-dimensional motion. With constant acceleration. Now we have already studied this motion. We know that the displacement of the object at a given time is nothing but the average velocity, which we can say that the initial plus the final divided by 2 times the time it takes. And we also know the change in the velocity, which we define as v final minus v initial. Since it's motion with constant acceleration, this is just acceleration times gravity. So we can eliminate delta t from these 2 equations, and that will give us delta x is equal to 1 over 2 vi plus vf times v final minus v initial divided by the acceleration. Or acceleration times delta x, this is equal to 1 over 2 v final squared minus v initial squared. Okay, this is one expression that you probably already know. Let's do a few more steps with this one. We already know that acceleration in one dimension, we don't have to write the vector signs, everything is a number. So acceleration is force divided by the mass. So if you just put it over there, we have the force times delta x is equal to 1 over 2 mv final squared minus 1 over 2 mv initial squared. Or we can also say that f times delta x, the displacement, is equal to the change in 1 over 2 mv squared. mv squared. So for example, if this was a one-dimensional example, we have a constant force. If you wanted to obtain how much the velocity of an object changes, it's enough to know this much. So we know that the change in the velocity squared times these factors will be equal to the force acting on the object, which in this example we assume to be constant times delta x. How much time will move? We don't need to know how long it takes to move that distance. We don't need to know what it made meanwhile. The only thing we need is what is the displacement, what is the constant force acting on it, and that will give us a change in the velocity. So there are two combinations that will appear quite frequently. What is this one? This combination will be important. And the other one is this one. This combination, the force times the displacement. Today and next week, we will be mainly talking about these two things. But this is just a one-dimensional example we already studied. Let's see how this would generalize to 3 dimensions. Let's just imagine. Let's do another example. And let's see if this is generalized to 3 dimensions. Now, one example that we can see that we have already studied is the projectile motion. So let's imagine that we have an object moving under the influence of gravity. This is the initial velocity, v0. And we have already seen that the vertical motion and the horizontal motion, there is independent motion. Horizontally, if you just there is no acceleration, let's say this is our x-axis, the horizontal direction. Let's just choose it as x-axis. The vertical direction would be the y-axis. There is no horizontal acceleration, so the velocity, horizontal velocity is just constant. Delta v1, vx. The change in the x component of the velocity will be 0. Now, if you look at the motion in y dimension, it's again just one-dimensional motion with constant acceleration. We can just use this result straightforwardly. We have to, of course, identify this displacement as the displacement in the y direction. The displacement in the y direction. Well, this time the force, we are looking at the y motion in y direction, so the force is only the force component of force in the y direction. This is equal to the change in 1 over 2 mvy squared. So here, since it's a 3-dimensional or 2-dimensional motion, it's just 2 independent 1-dimensional motion, we can just use the result from 1 dimension for both of the coordinates x and y. And these two expressions still hold. Now, these expressions are not that nice. The main reason is that, you see, these coordinates, it's just, I chose those coordinates, they're arbitrary. I could have chosen some other coordinates. But if I had chosen some other coordinates, this would be different, fy would be different, delta y would be different, or everything would be different. So I don't really know how this equation would modify if I change the coordinates. I would rather write these two equations in a form that will be independent of the coordinates I choose. Now let's see, I can also write the change in x. So the fx times the change in x. This is equal to the change in 1 over 2 mvx squared. This is also true. Well, Vx is just constant, so there is no change in Vx. The change in Vx is 0, so the change in Vx squared is also 0. What will change in 1 over 2 and Vx squared, it doesn't change during motion. Fx is 0. This is also 0. The left hand side is 0. The right hand side is 0. Let us just look at it. We have fx delta x plus fy delta y. This is equal to delta change in 1 over 2 and Vx squared plus Vy squared. Now what is Vx squared plus Vy squared? It's v squared. It's the magnitude of the velocity. It's the speed of the object. Now the nice thing about this combination is that the speed of the object is independent of which coordinate I choose. So if I rotate these coordinate axes, okay, I will have a different Vx, I will have a different Vy, but Vx squared plus Vy squared will be just the same. It will not change if I rotate the vector. The length of vector will not change after rotation of the coordinates. So this is nice. So this expression, delta 1 over 2 and V squared, is independent of which coordinate I choose. So if I can talk about this object without referring to any coordinates. Now that's a nice nature doesn't really care about the coordinates. It's only us who wants to pick up one coordinate to do the calculation. Now let's look at this one. Does it ring any bells? Look at this. Let's take a look at some vectors. What did we do with vectors? What kind of manipulation we did with vectors? We multiplied out the numbers. There is no number multiplication here. We solve the vector. But the nice thing about the vector is that the vectors exist whether we choose the coordinates or not. Only if we want to talk about the components of vectors, we have to choose the coordinate axis. Now in this problem, we already have two vectors. One is the force vector. It is fx in the x direction plus fy in the y direction. The other one is the displacement vector. This is delta x in the x direction plus the delta y in the y direction. So can I relate the left hand side to these two vectors? It's a scalar product. If you remember how we define the scalar product, it is just multiply the x components, multiply the y components, multiply the z components if they exist, and then sum them up. So here I have x component of the force times x component of the displacement vector plus the y component of the force and the y component of the displacement vector. So it is in three-dimensional, at least in the projectile motion, we also know that f times delta r, this is equal to 1 over 2 and v squared, the change in 1 over 2 and v squared. Now let's do one more example. Now this is a bit different. I mean, if you look at the one-dimensional piece, it is the force times the displacement. Now the way, at least in this example, how we generalize it is that we are just taking the scalar product of vectors. Now one possibility could have been when I just multiply the magnitudes. That would also be a possibility, but at least in this example it doesn't work. If we use the scalar product, in that case it works. Now let's see another example whether this scalar product is in general valid or not. Let's imagine we have this mass M, and we got the force on this mass M in this direction. This is the force. It makes an angle theta with the horizontal. Let's also add some friction. It is moving, so let's assume it's the kinetic coefficient of kinetic friction in between. What will be the acceleration? Now, of course, it will be motion with constant acceleration, and for motion with constant acceleration, the motion will still be one dimensional if the object will be moving in one direction. So we will be able to still use this relation, but first we have to identify what the acceleration is. So we have to find first the acceleration of this mass. Let's first draw the free body diagram. Now what are the forces acting on it? There is the F, there is the weight, there is the friction force, there is the normal force. Any other force? No, let's just ignore the drag force for the time. We only have the friction force. Or you can also say that the drag force is included in this friction force. I will not be using this expression. Okay, so what is the total? Let's choose some axis, X and Y. Okay, the total force, just at the angle of theta. Or let's start with F. What is F in terms of its components? The horizontal component will be cosine theta. It's in the x direction. And the vertical component will be F times sine theta in the y direction. Now we can write the total force acting on it. Okay, along the x direction, we have F cosine theta minus the friction force, the magnitude. This is the component of the friction in that direction. Along the y direction, we have F sine theta plus the normal force minus mg. So this is the total force acting on my object. So my object is moving only in the x direction, so there's no acceleration in the y. And y should be equal to 0, but that basically tells me that Fy should be equal to 0, which just means that F sine theta plus m minus mg should be equal to 0, or the normal force is mg minus F sine theta. In that case, the total force is just in the x direction, F cosine theta minus F friction. This should be equal to m times a in the x direction. So now we know the acceleration. The acceleration of the object in the x direction is F cosine theta minus the friction force divided by the mass. Now we can go back to our one-dimensional example where we related the displacement in one dimension, multiplied with the acceleration in that dimension. So 1 over m F cosine theta minus F friction times delta x. This should be equal to 1 over 2 and dx squared, the change in that one. Now the Vy doesn't change, so the change in Vy squared is also 0, so I can just as well write this as 1 over 2 m V squared. 31m. Now let's move the m to the other side. So we have F cosine theta minus F friction times delta x plus F sine theta plus n minus mg delta y. This is equal to the change in 1 over 2 m v squared. M is over here. This is the acceleration. So acceleration times delta x is the change in 1 over 2 v squared. And here I have the m over here. This is the initial expression we obtained. Then if we move the m to the other side, this is what we get. How? By v squared. Okay, then here are one more step. This is equal to the change in 1 over 2 vx squared plus 1 over 2 vy squared. Because vy doesn't change. So the change in vy squared is just 0. I just add a 0 over here. The reason why I added that is because vx squared plus vy squared just comes to v squared, which is independent of which coordinates I choose. Now vx depends on my coordinates. If I choose a different coordinates, my vx will be different. But vx squared plus vy squared will not depend on my coordinates. The second line, okay, this is the term that we have over here. I multiply both sides by 10. And then I added this one. This is the y component of, this is the x component of the total force acting on my object. This is the y component of the total force acting on my object. That the y is the displacement in the y direction, that x is the displacement in the x direction. But I could add this term because I already know that this is 0 and this is 0. Both of them are 0. So this term over here in my system is always 0. There is no y displacement. So I added 1 0 on the right hand side and another 0 on the left hand side. And the reason why I did this is that if you look at this expression, that is nothing but f total dot r. Or I can also write this as f plus f friction dot of this delta r. This is equal to the change in 1 over 2 v squared. But the total force, there is of course a normal force, but normal force doesn't contribute because normal force is vertical, but our displacement is horizontal. So there is no contribution. When I take the scalar product with that r, there is no contribution. And the weight similarly it doesn't contribute because the weight, the force due to the weight is pointing downwards and the displacement is horizontal. So they are again 90 degrees at each other. So the scalar product is just here. So we have at least these three cases in which the change in this expression is equal to such a scalar product, the total force times the displacement of my object. And this is general true. Now these quantities, 1 over 2 and v squared, this is what we call the kinetic energy. Why kinetic means because it's related with the motion. If the object is moving, it has what we call the kinetic energy. Now the other part, F dot delta r. This is what we call the work done by a force F. Constant force then. It is important that the force should be constant if you want to use this expression. Otherwise, the work done will not be equal to this one. But if the force is constant, we have already seen 3 examples of constant force where the change in this one was related to the work done by all the forces acting on my object. change in kinetic energy is equal to the work done, the total work done on my object. Now this definition of the work, and if you remember the definition of the scalar product, this is nothing but the product of the magnitudes multiplied by the cosine of the angle between the two. Now these two factors are kind of intuitive if you just think of your everyday use of the word work. If you are carrying a heavy load, if you want to push an object, a heavy object, you will think that you are doing more work than if you are pushing a light object. The difference is that in one of them you are exerting a larger force than in the other case. So the more force that you have to exert, the more work that you will be doing. This was kind of, it's intuitive, let's say. It's expected. The other term, this delta R, is also expected because if you assume that you are pushing an object, if you push a heavy object 1 meter, or if you push a heavy object 2 meters, you will say that you have done more work pushing an object 2 meters than the work that you have done by pushing it for 1 meter. This is also in that sense intuitive. This is kind of not so intuitive. Now, a few confusions about that part is, let's suppose you are carrying this book. You pick up your book and you hold it, and you carry it around with constant speed. So what is it? Are you doing the work? So according to this definition, you are not doing any work on this book. Because the force that you are exerting on the book is vertical. But the displacement of the book is horizontal. The angle between the two is 90 degrees, cosine of 90 is 0. So there is no work that you are doing on this book. Then why are you getting tired?
That is the question.
Yes. Why are you getting tired? And with this book you get tired quite fast. Okay, you see, if you were one of those working animals that could block, let's say, these joints, if you could block this one, I wouldn't be doing any work and I wouldn't get tired. So if you just block my hand just like this, and put the book blocking my hand somehow, I will get tired. Although I'm still exerting the same force. Now this is the question. When you hold this book like this, let's say you forget the displacement. According to this definition of the work, you are not doing any work. There is no work done.
Because of the net force on the object is zero.
No, I mean, okay, that is another confusion about the work. You can talk about the work done by an arbitrary force. It doesn't have to be the net force. But I am exerting a force on this book. That is not the net force. I am exerting this force. Nevertheless, I'm not doing any work on this book. Of course, there is the work done, there might be work done by the gravity, there might be the work done by my hand, but none of those two forces are doing any work on this book. But if I'm not doing any work, I get tired. Why do I get tired?
Because of muscle construction.
Well, this question is in fact not related about physics. It's mainly related with other phenomena. It's related with biology. How do your muscles work? How? Well, your muscles are never at rest. Even if your hand is at rest, the molecules in your muscles are never at rest. So they're kind of, you have these two kind of molecules, let's say not even cells. These molecules are inside the cells. They constantly contract and release themselves. They contract and relax, contract and relax. So when you are holding it at rest, It's basically they contract and relax in such a way that your hand doesn't move. But this contraction and relaxation, this constant contraction and relaxation, they do work. Basically, your muscles are doing internal work. They are not doing any work on the book. And since they are doing internal work as you are holding this book, that's why you get tired. But still, you are not doing any work on the book. Okay, another point of confusion is this. Okay, I'm holding it like this. Am I doing any work? Am I doing any work on the book? No. Let's assume I'm in the elevator. I hold this book like this. And the elevator is moving up at constant speed, at constant velocity relative to Earth. Am I doing any work? I am doing work. Am I exerting a force on the book while I'm holding it like this? Yes, I am exerting some force in the vertical direction. If I'm in the elevator and you are observing from one side, is the book being displaced? Is it being displaced in the vertical direction? The force is in the vertical direction, the displacement is in the vertical direction. So there is a positive work done because cosine theta is just 1. So the work done is nothing but the product of the magnitudes of the displacement and the force that I exert. So there is a net work done. Now let's imagine one more thing. Let's imagine that you are also riding with me in the elevator. So you are also an inertial reference frame, and you are making the observation. So we have these two observers. One observer is outside. He sees me holding this book like this, and getting tired. And the elevator is moving up, and he tells me that I'm doing some net work. And then you are in the elevator, you observe me, I'm still holding the book like this. So do I do any work in your reference frame? No. In one reference frame, the book is being displaced in the direction of the force. In the other reference frame, the book is not being displaced. So this is another thing. The work done depends on which reference frame you are using. But that isn't that a problem? So we have already said that the change in 1 over 2 and v squared is equal to the work done, the total work done on the object. And we just said that the work done, this part depends on the reference frame. This part is also reference frame dependent. So if you go to another reference frame, most of the work might change, might not change. The work done might change, but the speed will also be different in general if you work with the reference frame. So both the left-hand side and the right-hand side will be different in a different reference frame, but the equality will not change. Any questions?
There is a friction in communication, for example, and can use the friction force.
So in this example, I'm holding this book, moving it around, there is a friction force doing any work. Is there a change in the energy? That's not change, I'm moving at constant speed. So that's v squared change. So v squared is constant. So there, the total work done on this book is 0. Now, of course, we can say that, okay, we have there the atmosphere, there is the drag force acting on this object. So if I'm moving like this, the drag force will be pushing the book in the backward direction. And then there should be the friction force pushing it in the forward direction. The friction force does some work. The drag force also does some work, but the total work will be 0. Now that brings us to another concept of positive and negative work. We can do positive work and also negative work. So you see, the work done is positive if cosine theta is positive. Cosine theta is positive if theta is, let's say, less than pi over 2. And W is negative if cosine theta is less than 0, and this is true if theta is larger than pi over 2 and less than, let's say, pi. So if you have this book, let's say if you are pushing it in that direction, then the data angle between this force and the displacement is it is 0. This is the direction of the displacement. This is the direction of my force. The angle between the two is 0. So the work done is by my hand on the book is 0. Cosine theta will be it's positive. Theta is 0, cosine 0 is 1. So the work done by me is positive. Now at the same time there is friction acting on it. I am pushing this at constant velocity. I am doing positive work on the book, but the friction is in this direction. The displacement is in the other direction. The angle between the two is 180 degrees, and cosine of 180 is minus 1. So the work done by friction is negative. So there's positive work done by my hand. There is negative work done by the friction forces, and they sum up to give me 0, so that this relation still holds. The speed doesn't change, so the total work should be 0. The work done by me is cancelled by the work done by friction.
We said that when we are in an elevator, there is a constant speed, and we are going to move.
Okay?
And we are going forward.
No, we are not doing
We are not in an elevator, we are not going.
in elevator, if the elevator is going up, we are doing positive work.
Its velocity doesn't change.
Its velocity doesn't change.
Net work is 0.
That work should be 0. What is the other work?
Elevator, there is force acting for gravity.
Okay.
There,
So gravity is pointing downward.
but if you apply force,
The displacement is upward, so the work done by gravity is negative. The work done by my hand is positive, the work done by gravity is negative. Okay, the elevator is moving downward. I'm holding it like this. Underneath it. I am doing minus work on that side. Okay, the outside observer will see that I am exerting a force in the upward direction. The displacement is downward, so I will be doing negative work. But the weight of the object, first due to the weight, the force is downward, the displacement is downward, so the weight of the object will do positive work. And again, the sum of the two will be 0.
Why do you find work as force multiplied by the displacement?
Well, it just arises in our analysis over here. There's in both of these analyses where we have this, we are exerting a force on the mass with an angle, and we were studying the projectile motion. In both of them, we had seen that the change in the kinetic energy was equal to the force acting on my object, scalar product with the displacement vector. So that is the combination that always arises.
What does it mean for negative?
Okay, so if you just look at this relationship, a positive work will mainly cause the kinetic energy to increase. So if you are doing positive work, in a sense the force is giving kinetic energy to the object. Whereas if the work is negative, the change in the kinetic energy will be negative, so the kinetic energy is decreasing. So if you are doing negative work, you are taking away kinetic energy. Or if you are doing negative work, you are trying to stop it. Let's just imagine you are just running towards me and I try to stop you. I just push you This one. This combination again arises, and we just give it the name kinetic energy.
Combination between mass and velocity.
Yeah. It only depends on the velocity, so it's only related with motion, so that's why we call it kinetic.
So what is the difference between the difference between this kinetic energy and movement?
We didn't define it yet, so we will come to that point. For the time being, just know that there is this nice combination, which we call the kinetic energy, and the change in this kinetic energy is related to the work done on the object. Yeah? Well, let's see, what does this tell us? It tells me that if the work is negative and the kinetic energy, which depends only on the speed. So the speed should be lower if there is negative work. Again, this relation is valid for the total work. And if we are calculating the total work, some of the forces acting on the system can do positive work, some of them might do negative work. But as long as the total work done is negative, the speed has to decrease. If the total work is positive, that means the speed is increasing. Do you have a question? You see, one thing we said about the work is that it depends on the reference frame. So what is the reference frame? You want to, okay, you want to go to a reference frame, let's say, that is fixed on the sun. That is also an inertial reference frame. Oh, good enough. In that reference frame, if I'm holding this in my hand, here, in the other reference frame, of course I'm moving, and the work, I will be doing some work. And you don't even need to go to the sun. You can take the elevator and just start moving upward with the elevator. I'm not changing anything. You are moving with the elevator this time. I'm outside. You are the observer in the elevator. And in your reference frame, in the reference frame fixed at you, I am doing some negative work if you are going up. If you are going down, I will be doing some positive work. Again, work always depends on the reference frame. If you go to another reference frame, the work will have a different value. Just like the speed depends on your reference frame. If you change your reference frame, the speed will also have a different value. We are assuming that the elevator is moving at constant speed. Okay, let's write it down. So initially the elevator is, let's say, here. You are holding the book. And then the elevator is moving at constant speed, at constant velocity. Not changing the position of your book. Now, what are the forces acting on the book? This is the book. There is a weight. The force due to the weight. There is also the normal force. Then your hand is exerting all the book. And what is the acceleration of the book? It is 0. The acceleration is 0. But that means the total force is 0, acting on the book. The total force is the normal force plus the weight. this should be equal to 0. So the normal force is equal to minus the weight. Now the work done on the book is the total force acting on the book. This is the change in the kinetic energy. Is equal to the total work done on the book by external forces, which is the total external force times the displacement. Well, the total force is N dot delta R plus W dot delta R. Now, this is the work that I am doing on the book. And this is the work that the gravity is doing on the book. And we know that since they are these two forces, the normal force and the force due to the wind, they have equal magnitudes, opposite in directions. If this is positive, this is negative. And they cancel each other. Exactly. Since we are doing a motion with constant velocity. They should exactly cancel. So the total work done on the book is exactly equal to 0. Well, that is the change in the kinetic energy because the book is moving at constant speed. Can you repeat it?
When someone chooses an object
Okay.
towards me, in motion, the body has a certain kinetic energy.
Okay.
And I stop it. I stop it at that point.
Okay.
And there is no movement at that point. So what is the work?
What is it?
Work done there.
Why would you? Okay, whenever you are talking about the work, okay, did you get the question? So he is assuming that somebody, me, I'm throwing some object towards him, and he just holds it, and the object doesn't move, right? Okay, first of all, what is the acceleration at that instant?
From a certain velocity, I can say the acceleration can be up to infinity.
Okay, you are putting the acceleration to infinity. And the displacement, you are saying that the displacement is 0. So that's kind of the question. But it is at 0 times infinity of circle. So that is an idealization. In real life, what will happen is you can exert a very large force, causing a very large acceleration, but nevertheless, the displacement will be non-zero. There will be it will be very small, it can be very small, but a very small displacement and a very large acceleration and hence a very large force. Their product will be a finite number, and it will be equal to the change in kinetic energy of the object. So this will still not change. And if an object is moving, you can never stop it by exerting a force at 0 displacement. So that force has to be infinite, and infinite force will not exist. You can only get close to it. Other questions? Okay, we can continue after this.